Hello, I'm Jeff Acevedo. My Grantham student ID number is G000349961, and this is my EE450 Capstone project, which I've called the Light Rider. I hope you enjoyed the product. I've had a great time making it, and I've really enjoyed this class. The purpose of this project was to increase rider safety while reducing waste. Now, this was going to be done through the generation of electrical current and a self-contained unit on my son's bike. I wanted to utilize recycled and/or salvaged items as much as possible to help reduce cost and to help reduce the waste. I wanted to avoid the use of disposable batteries, as that's just another waste that I didn't see as necessary. And I wanted to increase efficiency by using power that was already available due to my son pedaling his bike. The source of this project came about while I was doing my EE410 class, which was my technical project management class. I was tasked with coming up with a project design, and started thinking what I could do. And one day I was standing outside and my son was coming back, and it was dusk, or dusk had just set in, and it was kind of a little bit dark out. As he's pedaling his bike down the road, I could tell it was him coming, but I could also tell that it would be easy for a driver to not see him. He did have reflective equipment on his bicycle, but reflection only occurs when a driver actually has their headlights on him. So it became apparent that this could be a dangerous situation for him. At the same time, I was working on a project in my car using some electroluminescent wire, or L wire, and he saw it and thought it was pretty neat that the wire would light and glow. So we decided that it might be a good idea to outline his bike with the L wire. At the same time, we discussed the use of flashing lights. So I thought about the 555 timer, which in an astable mode can create a pulse. Well, as with any project being completed, there's going to be factors that are going to limit our abilities or limit the outcome of the project. One limiting factor, probably the largest, is the time frame. This is an 8-week course, which gives me 8 weeks to complete the class. Cost. Obviously, not producing something for mass production or going to make any money off of it. While the education is great, I did want to keep the budget down somewhat. So I set a budget of $150, and I did set this during my EE410 class. Size, being as this was going to be mounted on my son's bike, which is just a 20-inch youth bike, I needed to be small and lightweight. Safety, wanted to ensure safety. Obviously, we're not dealing with very high current or very high power, but we wanted to use low power to reduce shock hazards. And then the power source. I knew I wanted to use a motor, but I had to come up with what type of motor to use, and then I had to identify the voltage and current that could be obtained from the motor, and if that was going to be enough to drive my circuit. Well, the original block diagram, knew I was going to use a stepper motor, but initially I was going to take, it was a 2-core stepper motor, and initially I was going to take 1 core and send that to a DC rectifier onto the pulse generator and down to the LED circuit. The other core I was going to send to a step-up transformer. The step-up transformer was going to be a 5-to-1, which meant for every 1 volt I would get 5 on the outside. And I was going to send that to the electroluminescent wire, which needs about 100 volts AC in order to run. Came across some problems trying to use the step-up transformer. The DC rectifier, it was not able to get the current on the outside that I needed, so I went back to the drawing board. I then modified my block diagram, having the stepper motor send both poles to 2 separate bridge rectifier circuits. On the outside of that, I was able to couple those 2 voltages together and in effect double the DC voltage available. I took that DC voltage into a voltage divider and 5 volts ran to the pulse generator, which is the minimum requirement for a 555 timer, and on to the LED pulsing circuit. The other portion kept this 12 volts DC and ran that to a low current AC to DC power inverter that is sold specifically for electroluminescent wire. As that power inverter was only about $5 or $6, I thought this was a relatively cost-effective way to go. Plus, the power inverter was much smaller than the transformer I was initially going to use. Typically, a motor is driven by a current. As the current enters the inductive cores, it creates an electromotive force which drives the armature into rotation. The converse is also possible. If you take the armature of a motor, you spin it, you can induce a voltage into the inductive cores. In this case, I have 2 cores, and each would output an AC voltage. I found this graphic online at electronicsgurukumla.blogspot.com. I thought this was a very informative and a very easy way to depict how a bridge rectifier works. And as you can see, as the voltage goes positive, 2 of the diodes will pass the current, allowing the output to be felt across the load. And then as the voltage swings the opposite direction, the other 2 diodes pass the current to the load, creating another positive pulse. These pulses can then be fed to a capacitor to charge it up, giving us a good DC source. This page has the power supply section. It was developed in multi-sim, which this is a screen capture of. V1 and V2 represent the cores on the stepper motor. Each one is an independent AC signal. Coming off my motor, I had about 8 volts RMS, somewhere between 600 and 1000 hertz. Each one's fed to a separate bridge rectifier, and the outputs of those are independently stored on C1 and C2. C3 feels the full voltage of C1 and C2's output, which gives me somewhere between 12 and 16 volts DC, depending on the load and the RPM of the motor as it spins. Now, this graphic is a demonstration of a 555 timer set in astable mode. I found this online at www.technics.it. I thought it was a very good image that showed very well how a 555 timer works. As you can see, the voltage develops on C1, and as the voltage goes positive, it comes in on pins 2, which is your trigger. It sets the 555 into motion. The output is on pin 3. The pulse repetition time and the pulse width are determined by R1 and R2. In my final design, I replaced R2 with the potentiometer so that I can vary the PRF and the pulse width. Now, this is the actual circuit that I designed in multi-sim. This comes off of the voltage divider, which was given voltage by the power supply section. R2, which you'll see on the next slide, is the bottom portion of the voltage divider. Somewhere between 3 and 5 volts DC is provided to this resistor. That input is provided to the trigger voltage, which is pin number 2. And as stated on the previous slide, the 555 timer will create a square wave output when it's set up in astable mode. Now, this is the final completed circuit that I designed in multi-sim. To the far left is the power supply section. V1, V2 is the stepper motors, each core, running through my bridge rectifiers, and then The output of that is felt across C1, C2, and C3. The output there is, as I stated earlier, about 12 to 16 volts DC. It runs into a voltage divider set up by R1 and R2. R2 receives somewhere around 3 to 5 volts depending on the RPM. I did change out R4. I replaced that with a potentiometer, and that allowed me to adjust the speed of the LEDs as they flashed. The green section simulates the AC to DC power inverter. Multisim didn't have an AC to DC power inverter, so I used a voltage controlled voltage source. And then the X1 represents the electroluminescent wire, which is in effect a 120 volt light. And this was the virtual breadboard that I created in Multisim. I actually found the physical breadboarding a bit more rewarding and actually a little bit easier to complete. However, it's good to know that I can create a virtual breadboard in Multisim and know that my circuit's going to work the way that it's supposed to. This components mirror what you'll see on the next slide, which is my actual physical breadboard. This is a photograph of the actual breadboard that I created. To the far left are my two bridge rectifiers. Their outputs go to the dark blue capacitors. One is C1, the other is C2. The light blue capacitor, that is my 4700 microfarad capacitor, that was C3. The two resistors in the middle of the board are my voltage divider. Their outputs go to the electroluminescent wire, which the wiring is not in this picture. I had removed those wires when I took this photograph, but they would have been across the top rail and the bottom rail. That would have been a full 12 volts DC. The other portion goes to the 555 timer. The output of the 555 timer goes to those LEDs there. And my final circuit, I ended up using 4 on each side. I found that they could sufficiently drive 4 LEDs on each side.
Hello and good evening. My name is Jeff Acevedo. Grantham ID number G000349961. I'm in my garage. We're going to demonstrate the operation and initial testing of my light miter circuit, which is here. I have my drill, which is going to simulate the driving force of the bike that would normally be connected to drive the motor. I got a multimeter, and then I have my output, which is 2 sets of electroluminescent wire, and then the LED circuit. For this circuit, the output of the stepper motor is going to drive 2 bridge rectifiers. The stepper motor's output is going to be an AC voltage. One pole of the stepper motor, as this is a 2-pole stepper motor, will go to the first bridge. The second pole will go to the second bridge. I've used blue-orange coupled with blue and white and orange and white wires for the AC outputs. The output of the bridge rectifiers will drive a capacitive circuit to provide the DC voltage that will be fed to the voltage divider here. A portion of the voltage divider will go to a DC to AC power inverter. The other portion will go to the 555 timer that will output to the LED circuits. Power voltage coming off the DC to AC power inverter will be used to light 2 lengths of electroluminescent wire. This final circuit will be placed on a PCB board. The electroluminescent wire will outline my son's bicycle, and the LED circuits will alternately flash for high visibility.
Well, these photographs show the components placement on the PCB. That PCB is about 5 inches by 2.5 inches. As you can see, everything's set up very similar as to how it was on the breadboard. However, I did move the 555 timer closer to the capacitors just to make everything fit inside my enclosure. I set the potentiometer off to the side so that it was easy to get to with a screwdriver if we wanted to change how the lights flashed. The picture on the right is the bottom of the board. As you can see, I used a PCB that only had the foil around each independent hole, and I bent the leads over and then I soldered the leads together. Well, once I got most of my components soldered onto the board, at least the ones that would affect operation, I wanted to test the circuit and make sure that it worked, make sure that I had connected everything properly. At this point, I had one minor change to make. I had connected one of my power leads coming off of the voltage divider in the wrong spot. I ended up having to move that. I moved it, identified it very quickly, and then everything worked fine. The LEDs, I left those on the breadboard up until later on when I mounted those on their own PCB board. Overall, at this point, everything had gone very, very well. Probably about 2 hours or so of soldering and getting all the components located properly. Here's another photograph of the circuit. On the left side is a close-up of the same circuit from a previous slide. I just wanted to show the items in a little bit closer so you can get a better feel of how everything was laid out. The resistors in the middle of the board are the voltage divider. The resistors across the top of the board are the outputs to the LEDs. The resistors to the bottom right are the biasing voltages for pin 7. The capacitors, those are C1, C2, and C3. The smaller capacitor is the capacitor that goes on pin 2 of the 555 timer to create the charging. The green wire coming off of the 555 timer is pin 3. I like to use green for outputs. I generally try to use red for power and black for grounds. The picture on the right shows the mounting of the electroluminescent DC to AC power inverter, and then the plate there is the very back plate of the project box. You'll see this in another slide. Alright, well here everything is wired up and placed inside the box. Everything is tightened down, screws are in place, wires are routed, spot tie is in place. Use zip ties to keep everything nice and neat, and also in case the wires get pulled from the outside, I set it so that they would not allow the wires to get pulled off the board. As soon as that cover gets placed on there, this thing's ready to go on the bike. Well, I found the perfect mounting location for this was underneath the back side of the seat for the bicycle. At that location was the reflector. I used the reflector bracket to mount the bike, or mount the project box. And then I just took the reflectors piece and I glued it right on the front of the box. Fits there perfect. It's out of the way. Wires are tucked in nice and neatly. And it actually looks pretty aesthetically pleasing. In order to get the proper rotation on the motor, I needed to determine how big of a wheel I could use to drive against the outside of the bike tire. I went online and found that the average speed of a youth bicycle is anywhere from 4 to 7 miles per hour, some a little faster, some a little slower, but I figured that using 4 miles an hour was a pretty safe bet. At the max rotation of my drill, I get 600 RPMs, which converts to about 10 revolutions per second. At 4 miles an hour, I determine that's 5.9 feet per second, or 70.4 inches per second. The 20-inch tire has a circumference of, you multiply the 20 by pi, is 3.14, and you get 62.8 inches approximately. So you took the 70.4, divide that by 62.8, and I get a 1.12 is the number of revolutions that this would make in 1 second at 4 miles per hour. And that's approximately 1 revolution per second, which is the number I went ahead and used because it's so close. To obtain the 600 RPM, the ratio of the bike tire to the mount, or to the motor wheel needed to be 1 to 10. I just so happened to have a wheel in my garage that was 2.5 inches. It was rubber. It was going to fit in there perfectly. I figured that out as a ratio of 1 to 8. And during my testing with my drill, I found that the voltage levels were sufficient, about 65% of the drill's power. So that's a 1 to 6.5 ratio, and an RPM of about 390 RPMs. So at that time, I determined that the 1 to 8 ratio using the 2.5 inch small wheel would be fine for giving me the power that I needed. This was actually a pretty fun part of the project. Everything that I used to mount my project to the bike was readily available in my garage. I generally work on projects on a regular basis, and I have a drawer that when I have extra spare random parts, I toss them in there. The bracket was off of another project that did not need to be used. The wheel, like I said, that was off of a caster that I had sitting in the drawer. The only piece of hardware that I did have to purchase was the coupler for the motor shaft, to go from the motor shaft to the wheel. I attempted to build one. The one that I built, the hole was slightly off center, and because it was slightly off center, it caused the wheel to wobble a little bit. I found this, which was a 1/4 inch to 4 millimeter adapter, and it only cost me about $3 or $4. So I thought that was money well spent. You can see some of the electroluminescent wire there. I mounted that with zip ties Flag zip ties works great. Everything's out of the way, tucked in neatly. Well, here's some final pictures of his bicycle with the electroluminescent wire on both the left and right sides. And the center picture there, you see the two rows of LED lights. They'll alternately flash left versus right. Mounted everything up. It was good to go. Nothing loose hanging in the way. No danger of catching anything on the pedals or the chain or anything like that. I was pretty satisfied at this point.
For the final demonstration, I enlisted the help of my son, Joshua. This is his bike, and it was for him that we did the Light Rider project. All right, Josh, when you're ready, go ahead and start pedaling. As you can see, he's got the blinking lights on the front. That's a result of the 555 timer's output. The L wire is being powered by the power inverter. Everything's powered through that wheel being driven by the back wheel. Spins the shaft on that stepper motor. Output from the stepper motor goes into the box, which houses the circuit. And here's the full effect. This is what it looks like in pitch black.
Well, here is a screen capture of the Excel spreadsheet I created for the cost of the circuit. Some things to note: the stepper motor, the 2-pole 4-wire stepper motor, the $8 is what it would normally cost to purchase a stepper motor. I was able to buy mine on eBay in a lot set. I got it for quite a bit less than that, so my actual project cost was a little bit less. Probably would have cost me about $3 if I broke it down for the lot of motors that I bought. Everything else is pretty much what I spent. Some of the capacitors and resistors, those are the prices if you're going to purchase them. I actually tinker on the side, so some of those were in drawers that I already had. The only other additional cost would have been a hardware cost, and that was for that one coupler that I spoke of, that connected the motor to the wheel, and that was $4 and some change shipped. So all in all, I spent less than $70 on this project, and I did set a budget of $150. So as far as I'm concerned, the project was completed on time and under budget, so it was a success. Again, like I said, this was a great project. I had a lot of fun. My son loves this bike. He loves being able to pedal around. The demonstration in the dark shows just how much enjoyment can be had from this. And I thank you for your time, and I hope you enjoyed the project.